Okay, so as the last speaker of the session and of the day, I have the tough job to keep you awakened. So I will try to do my best. And I will talk about some ways of constraining seismic attenuation in the Deep Mantle. This is a work I've been doing recently from being a mineral physicist. Let's say I was trying to collaborate with seismologists, so I will be talking quite a lot about seismology. So my collaborators here, Stéphanie Durand, who just recently defended a PhD thesis in Lyon, Ved Lekic, who was speaking this morning, and then two other collaborators that you know, Yannick Ricard and Barbara Romanowicz. So first of all, you saw this morning the seismological tomographical model that Ved Lekic was showing from Ritzema et al. That shows the evolution of the red and blue zones seen by seismologists. So blue zones, the fast zones, and the red zones, which are the slow zones. And from the, let's say, geophysical point of view, in terms of, as a function of depth, you would like to know what these regions are made of. So the question I will try to answer is how can we improve the constraints coming from interpretations of tomographic images. So basically the question is how one can go from seismic velocities, which are the direct observations on the structure of the deep mantle, to density, temperature, and composition, which are the model parameters. And these 3D interpretations of tomographic images, it's a story that go back to the 90s, and the question not only talking about density and temperature, but also involving composition was, for example, in papers by Suen-Zewonski and Masters and al. But over the 15 years since that time, there was many other works on this subject. In order to do the interpretation, one needs to know quite precisely what I call here the conversion factors from seismology to mineralogy. And what the conversion factors are, basically those are the partial derivative of the seismic velocities. So one way is from the observation, you go this way here. Using these two conversion factors, you can obtain lateral variations of temperatures and lateral variations of chemistry as a function of depth if you take the tomography at each depth. Here I show the results from the study by Jeannot Rampert in 2004, who at different depths derived variations of temperatures, variations of perovskite content, and variation of iron content in the assemblage. What he did in this work was that he clearly showed that there might be a long wavelength chemical heterogeneities in the mantle that would correspond to a tomographical images. Of course, you can go also the other way around, so using some synthetic partial derivatives, assuming some temperature variations and chemical variations, and to produce synthetic tomographic images. And we did this with Yannick Ricard. We did just a simple model having a subducting slab going into the mantle, and then we were trying to convert it into tomographic images. But in this case, these partial derivative was taking into account the phase changes that are taking place at different pressures and temperatures in the mantle. And you can see that from a simple temperature profile, you can get quite a complex tomographic image, together with here, for example, we were trying to simulate the effect of the subducted crust so having also the variation in bulk composition. The two previous pictures I showed you, those were purely elastic interpretations of the tomography. But we know that the real mantle, there is a seismic attenuation. Just to make sure that we all talk about the same thing, I want to recall that there is what we call extrinsic attenuation and an intrinsic attenuation. So the extrinsic attenuation is, so for example, it's like a geometrical spreading. Of course, I know that the seismic wave is not like the wave on the surface of the water, but it just shows you that the amplitude of the signal is decreasing because we have a conservation of energy, and the geometrical spreading makes the amplitude going down. Then we have seen also over the day that the focusing and defocusing, means scattering, due to the heterogeneities in the mantle may be important, and it also introduced some kind of attenuation because the incident wave, there is some part of the energy that can be scattered back, and so what you record after the heterogeneity, the amplitude may change, but that's not what I will call the intrinsic attenuation, and what the intrinsic attenuation, that's what I will be interested here now. So that's what I will call, let's say, the material anelasticity, which may be related to dislocations on diffusion mechanisms, and Patrick Cordier was talking very well about this this morning. The important thing is that when you consider the intrinsic attenuation, that you have to have some dissipative processes, and it's a long story already from the 60s, and there is many different dissipation mechanisms in the mantle, and I just want to use an example of diffusion to show what happens, how this energy is dissipated, that you have some material with some, for example, impurities in there, you have some external gradient there, then there is an incident seismic wave which makes move these atoms in the crystal net, and then the impurities can move. But in order to open this passage, it costs some energy, and this energy is taken from the elastic energy of the wave. And then, of course, after the wave goes away, there is a global entropy increase in the system and decrease of the elastic energy of the wave that goes out of the system. So usually what one has to do for each dissipation mechanism to describe, to characterize it by a characteristic time, this tau, and this tau is dependent on what we call activation enthalpy, and I will talk a little bit about this later on, and you will see this H star later on too. In order to characterize the intrinsic attenuation, we use quality factor, which is a big Q, or an absorption, which is a small q. So sometimes I will show a big Q, sometimes I will show small q. So high Q means low absorption. And what you need to realize that the attenuation, intrinsic attenuation, can be frequency dependent, and the frequency dependence is characterized by this alpha factor here. And then the thermal activation I showed you just before. So when you want to model this intrinsic attenuation, you need, of course, to know the elastic background of the material, so kappa and mu, the elastic parameters, and then you need to know q kappa and its frequency dependence, and q mu and its frequency dependence. Well, in the Earth, we already know that the q kappa, the compressional attenuation, is much smaller than the shear attenuation. So I will talk quite a lot about the shear attenuation here. So what do we know, or let's say what do we think to know about the attenuation in the mantle? So in terms of 1D models, You can, I just plot here few classical 1D attenuation models, PREM, QM1 from Widmer, QL6 from Durek and Ekström, QLMNF from 9 from Lorenz and Weissession, and QHR from a recent study by Huang and Ritsema. And if you see as a function of depth and the Q, so here it's 0, so here it's very elastic, and here it's very attenuating. Well, you can see that there is quite a scatter in terms of the deep mantle of the attenuation in 1D, that the different models varies quite a lot. Basically, what we can see here, that the deep mantle, the lower mantle, is less attenuating than the upper mantle. That's one good observation. But then in the lower mantle, we don't know if the attenuation is increasing, or if it's decreasing, as some models suggest. So this is the 1D view. There is, of course, attempts to map the attenuation in a 3D case, so lateral variations of attenuation, and the Berkeley group did a lot of work, and I just show here one example of from the paper by Gunk and Romanowicz, who mapped at the simultaneously the variations of velocities together with variations of attenuation in the transition zone at 450 kilometers, and you can see that the lateral variation of attenuation can be pretty high as 50% on the lateral scale. So, as I was talking about the conversion factors, what you need to know is that then if you want to transform, if you take the partial derivative of velocity in respect to temperature, there is an elastic part. That's what we used previously. But there is also a part that comes from the anelasticity. And this anelastic part had to be taken into account in a self-consistent way, because there is several parameters. There is the temperature. There is the G star or H star. It depends on the formulation you use. There is the Q, but these two parameters, the Q and H star, are intrinsically related, so you cannot just pick a seismic Q and then just play with different H star, because then it gives you a very inconsistent result. There is the frequency dependence of the attenuation. So all these parameters has to be known together in order to properly and self-consistently correct for the anelasticity when you try to interpret the seismological tomographical model in terms of temperature. I give you two examples of the effect of the attenuation. That one is from a study I made with Mark Bukovinsky a few years ago. We used a 2% seismic anomaly. It's just a test. And if you take a 2% seismic anomaly and you try to interpret it in terms of temperature, so these dashed lines here are the elastic limits. So the cold and hot elastic limits are not the same, because the elastic temperature derivative is slightly temperature dependent, so there is a slight temperature dependency. But then when you add the anelasticity in there, what you can see that in the case of the cold, fast velocity zone, the anelasticity does not do much. But it can do quite a lot in terms of the slow velocity zones. And here I plot the correction, the difference in terms of the activation as a function of the activation energy that we don't know, which depends on the different activation dissipation mechanism. But the key feature you should notice here, that in the case of the hot, slow velocity zones, a certain anomaly can be explained with a temperature variation which is smaller and can be by a factor of 2 smaller than what you would expect in the elastic case. So that's one important thing. The other is that there is a trade-off between chemistry and attenuation. And here, again, a very simple example, modeling some kind of plume-like structure in the mantle. So having a hotter structure in the overall, some kind of adiabatic or Brown-Shankland mantle. And then what I just try to do is from here, using my partial derivative to generate elastic seismic variations, anelastic variations, and then elastic, but including some chemistry in there. And you can see that the anelastic is very similar to the elastic plus the chemistry. So how one can distinguish between the two? So there's a question. So it's something that I'm working on now. So what I want to conclude here is that the intrinsic attenuation in the mantle cannot be, or at least should not be, neglected, and we need to know more robust. We need to have more robust constraints on the Q, on the attenuation in the lower mantle. So I will now talk about two possible ways how to do this. First one is from differential SCS minus S measurements. That's what we did with Stéphanie Durand. And then from analysis of distribution of velocity anomalies, and that's something that I'm working on with wet leakage here. So for the differential SCS minus S measurements, what I will now use a new parameter, a T star. A T star that is a integrated characteristic or integrated feature along the path associated with the wave, seismic wave. So you can see, this is the definition of the T star. What you can see is that if you are in a perfectly elastic material, so Q is infinite, so the T star will be 0. So the higher absorption, the lower Q, the higher T star. And now I will use not only one wave, but I will use two waves at the same time. I will use S and SCS, and then I will use those that are horizontally polarized in order to avoid some reflection, so that most of the energy is reflected at the core mantle boundary. And using the differential T times, so what I will call delta T stars, the advantage of this will be that it will screen mostly the deep mantle, and it will avoid the local structure, the surface structure close to the epicenter and close to the surface, because it's a differential measurement. So this will allow us, if we are able to measure the delta T stars, we will have a positive delta T stars, for example, in the case when we have low Q at the CMB. Low Q at the CMB, remember, is T star of SCS, which is high. So T star SCS minus T star S will be positive, because if you low Q at the CMB. If you have high Q at the CMB or low Q in the mid-mantle, it's the other way around. So the delta T star will be negative, because the T star of S will be high. So since you do T star SCS minus T star S, so it will be negative. Of course, since it's integrated measurements along two ray paths, you can also pick some information from possible lateral variations. So there is a mixture of two. There will be a mixture of some radial Q profile, but also lateral variations. You can take it also from the other side. You can look at this, for example, in the case of radial attenuation structure, the delta T star, you can compute some kernel for this attenuation, where here is a small q. And this is the kernel as a function of depth. So for example, if you have low q, which means high absorption, so what I said, you will have a negative delta T star, and as a function of epicentral distance of your measurements, you will screen your delta T star measurement will be sensitive to different parts of the mantle. So that's why I'm using this in order to screen the deep mantle. You can see that here there is no sensitivity to the Q in the upper part. just very quickly here, I showed you the methodology we use from a signal where we have the two waves, S and SES. We first compute an envelope that is amplitude-based measurements, and which is actually on the base. It is also background for the classical spectral ratio method. But in our case, we use a method which is called instantaneous frequency matching method. That is based on something that is called instantaneous frequency. If you have a sinusoidal signal, it's a one frequency, the instantaneous frequency will be constant at each time you look at your signal. Of course, this is not a periodic signal, but you can always look at one time, at one point, to the frequency of this signal. And what we will use as a hypothesis that for one event, if you compute the instantaneous frequency for S, it should be the same as the instantaneous frequency for SCS. Okay? Because it's one event, and we will assume that the frequency content will be same for all the phases. And so then we use some measurement procedure which is based on this operator, which takes into account both the dispersion and the amplitude decrease. And what we can then measure, for example, the instantaneous frequency of S and instantaneous frequency of SES. And on this signal, for example, we can see that the two are not the same. And so we will look for the attenuation mantle that will make these two instantaneous frequency same. So, for example, you can, this delta T star you will use here, and so it will change somehow the signal. If you use negative delta T star, it will change the signal in the other way around. So, for example, in this case, we would find, for this recording, we would find a 1.55 as a delta T star. We were also trying to compare different methods, the instantaneous frequency method and the spectral ratio method, and we have realized that there is some differences, and if we took some synthetic test, that we can clearly see that the instantaneous frequency method, or instantaneous frequency matching method, is much precise, it's much more accurate than the spectral ratio method, and then we can also identify some interferences and some other, let's say, features that can deteriorate the signal. So we did quite a drastic selection of the data we had, and we used three events. We had about 700 recordings for these three events, and we based our analysis on these three events. And I just show you the result for these three events here under the South America and here under Alaska. And here I show you the delta T star as a function of the epicentral distance. And we can see that we were able to recover some trends as a function of the epicentral distance. And we have used these trends and assuming that these trends are related to a 1D structure to make what I will call a regional inversion for a 1D model. And so those are the models that we had before, and this is the model that we have recovered from these three events. Which is interesting to see here that the model that we have recovered from these three regions, from the 700 recordings, is in its feature quite similar to that obtained by the Lorentz and Weiss session, but not the same amplitude. But it's still different from the 1D radial models. They are obtained based, for example, on surface waves and on normal modes, which are the gray models here. So the red models were obtained with body waves, and the gray models were obtained with normal modes. So we were wondering if this difference is due to the fact that it's a regional model only, because I showed you we had these three regions, or whether it is due to a frequency dependence of the attenuation. And assuming that, for example, it's a frequency dependent, we have some quite good indications that the alpha, which is by a lot of seismologists usually assumed to be zero, no frequency dependence of attenuation within the seismic band, we have recovered a positive alpha, which is quite in accordance with some previous results from the laboratory measurements, where the alpha was somewhere between 0.2 and 0.4, and we did also some work using normal modes, and we recovered alpha of 0.3, so it's not the same value, but what I wanted to say here, that the alpha is very likely not to be zero, different from zero. So within the seismic band, the attenuation is different from zero. Of course, this is something that can be useful also for, since you were asking the question to Motohiko Murakami, is that, for example, this kind of absorption band can be used for extrapolating the results that were obtained somewhere over there at the very high frequency with the Brillouin spectroscopy, to bring it back, or not back actually, bring it to the Earth and bring it within the seismic band. So if you know this kind of shape of the shape of the seismic band, then you can use it in order to calculate the mu or the Vs that you measure in high pressure Brillouin spectroscopy. So this was the first idea about how we can improve our knowledge on the attenuation in the lower mantle. So using delta T star, differential delta T star measurements. Of course, I could go in much details when I showed the figures, but I don't have time to show you all this. The other idea how to approach the attenuation in the deep mantle is related to the talk or to the approach that Vedlekic showed this morning. And I took this figure from his talk when he was doing the cluster analysis, and when he identified the two regions, the red region, which would be the slow zones, and the blue regions, which would be the fast zones. So the cluster analysis is here used only to identify the regions in the mantle where we see, or where all the models see something which is slower, and the regions where all the models see something which is faster. So then we look at the distribution of the velocity anomaly. So here, that's what it's here in gray. At the depths of 1,000 kilometers and at the depths of 2,700 kilometers. You can see, and it also Paul Takle showed it in the earlier talk, that at the 2,700 kilometers, the global density distribution is skewed towards the lower velocities, towards the smaller values of the velocity. Now I use the two clusters, or we use the two clusters, the fast cluster and the slow cluster, and we look at the density, at the velocity distributions within these clusters, how it looks like, and we plot it on top of this global distribution. And what you can see that at the depths of 1,000 kilometers, the two distributions are quite similar. They plot one on each other, but at the bottom they separate. And one important observation is that here you see something which is rather symmetric, but in the case of the slow cluster, it's not symmetric. The slow cluster remains skewed. So the global is skewed, and then within the global there is the slow one which is skewed, and the fast one which is not skewed. So we are saying, oh, that's something interesting. We should try to characterize this better and to see whether the skewness could not be due to the attenuation in the lower mantle. So we you can use this kind of normal distribution formalism or a skew normal distribution formalism, where in the skew normal distribution formalism you have two additional parameters. Of course, you have one additional parameter. You have, of course, the sigma, which is the width of the distribution, which will be similar to that in the normal distribution. But you have also a slant, which is related to the skewness, and you can compute by inverting, by fitting this distribution by this kind of function. You can compute the skewness, and we only find a significant difference from 0 for the skewness in the case of the slow cluster, or the velocity distribution related to the slow cluster in the bottom of the mantle. So we try to do it at each depth, and so we can look at this figure here. You see that in the fast region, depending, we use different tomographic models, we see that it remains more or less close to 0, depending on the model. In the case of the slow regions, we see that in the bottom of the mantle, all the models agrees that there is a negative skewness. So all the models are skewed towards slower velocities. So if it's related to the attenuation, how it could be related to the attenuation? So I come back to what I was telling in my introduction, is that we are going from temperature perturbation to velocity perturbation using our conversion factor, but the either elastic or inelastic conversion factor. So assume a perfectly symmetric normal distribution of temperature perturbations, and then if you use elastic hypothesis, so the k is equal to a constant, so then we will get again a normal distribution of velocity anomalies. If we use the whole inelastic, so the temperature towards velocity is not linear, it's a very nonlinear function, and then from a normal distribution you will not get anymore a normal distribution of velocity normal distribution of velocity anomalies, but you will have a skewed one, and the skewness is actually seen here, and here again is skewed towards the slower perturbation. So it works. It's a good working hypothesis. So again, it's a work in progress to show you even more the effect of the attenuation. So here you have an example of a distribution, slow distribution and fast distribution in the elastic case, and then we apply the inelasticity in there, and we transform these distributions. And of course, we can also pick as a parameter difference of temperature, because the inelasticity is very different on temperature, the difference in temperature between the two clusters. So matching the velocity distributions, we hope and we think, we believe, that we will be able to provide two constraints. First, on the Q in the lower mantle, and then the difference in the temperature between the slow regions and the fast regions. And we didn't do yet the inversion, but we pick at some depths at the very bottom of the lower mantle that was showing in a green, in black here, the real distribution. The distribution is observed by seismology. Then we picked some delta t and some q, some other parameters that I don't go to the details of the methodology here. And then we generated a fast distribution and a slow distribution, and then we add it, and then we find out that for some delta t and some q, we can get a very good match between the two. So the take-home message is that with using the delta t stars, we can obtain 1D regional models, I would say, based on body waves. and it confirms that there is a lower attenuation at the base of the lower mantle seen by body waves compared to those based on normal modes or surface waves. It can be either explained by the fact that it was a regional model, but we also think that it could be explained by a frequency dependence of Q. In order to obtain more information on the lateral variation of attenuation, we need to extend the analysis of the delta T star, having much better coverage. But as I said, the selection of the data was quite severe. And then we have used the analysis of velocity anomaly distributions, and we have shown that we will be able to obtain information of mantle attenuation, lower mantle attenuation, and the thermal structure. And on this second topic, I invite you to, during the AGU, to talk on Thursday, December 6th at 4:15 p.m. Okay, thank you very much.